So in this video, we'll pick up where we left off with forecasting trends. We've got estimating trend models in something like Excel or eViews or Stata or choose your favorite statistical software. R and Python are strongly recommended. Estimating a trend model with a quadratic trend or a linear trend in this case is easy enough. We just generate the variables that go on the right hand side and treat it like a regular regression problem. So I've already seen how to do some of that over here in Excel. I estimated the linear trend just by modeling orders here as a function of month here, and month is my easy peasy 1, 2, 3, 4, 5, just a regular count variable starting on the first month. And ideally, it would be nice if the first month was something like January, so it would line up with the calendar, but that's not even necessary. It can be whatever month was the first to be observed in this data set. Then over here on the right, of course, I've got some regression summary output corresponding to this linear trend model. I see that about 17% of the variation in terms of variance in the data is explained by just the month variable by itself. You see that in month 0, this model predicts about 90,000 orders, and each month this model predicts orders will be about $396 higher than they were in the previous month. Then of course I've got t-statistics, p-values, upper and lower confidence bands for each of these coefficients, as well as an f-statistic for the overall significance of the model, and the rest of my nice little pantheon of helpful statistics up here. I've got observations, the standard error of regression, so there's the standard deviation of the error terms from this model, adjusted R squared, which has a degrees of freedom penalty baked into it, and multiple R, which is just the square root of the R squared. Now, over here, I had created a new sheet where I regressed orders on month, and then down at the bottom, I went ahead and got the residuals from that analysis. Here's my predicted value for month 1, month 2, month 3, month 4. I see that the predictions are increasing by $396 every month. Here's the corresponding residual. So I see that, in fact, orders were about $12,422 less than predicted in the first month of the data set, but I've also got a 95% confidence band for these orders based on my prediction, y hat, minus 1.96 times the standard error of regression, which is all the way up here. There's the standard error of regression. That's how large these residuals are on average, give or take. And most of the forecasting is going to work in about this same strategy. If I want to predict the model, if I want to predict the data, at time t plus h, h is the forecast horizon, capital T is the last observation in the data set, as I mentioned in the previous video. So if I want to predict 1 month in advance, then, well, t is 48, my last observation, and then 1 month in advance would be plus 1. 48 plus 1 would be my 49th observation, which is, sure enough, something that I predicted right here. In order to put that model together, what do I say? I say, that day, the model will be beta 0 plus beta 1, whatever my time variable is, plus an error term. Okay, well, here's the predictable part. Beta 0 plus beta 1, the time variable. So I'll get estimates of those, and that will give me my point prediction. What is the unpredictable part of what happens on the next day? It's simply epsilon t plus h, which is the error term that happens in the 49th month. Each of these observations is pretty close to some true model that involves a trend, but there's always something idiosyncratic about a given month and a given observation that I'm not going to be able to explain. This predictable part of the model gives me my point forecast, and this unpredictable part of the model tells me how uncertain I am, so my 95% confidence interval is going to be based on the standard deviation of these epsilons, which is what we did when I calculated this confidence interval. My point prediction minus 1.96 times the standard error of regression, and for my upper bound, my point prediction plus 1.96 times the standard error of regression, which was all the way up here. Okay, so that's the general strategy, and it works for, observation 49, which is t plus 1. It works for observation 50, which is capital T plus 2. And it works for whichever observation you're interested in looking at as far out into the future as you want to go using this easy linear trend model. So for instance, if I'm feeling very ambitious, I can go ahead and click and drag as far down as I want to go until I say, there, in a couple of years, this model predicts that I will have way more revenue than I had today. So that's good news, but of course it's an upward sloping linear trend, so it's just going to keep going forever. Well, let's try another one. Let's go back to here. Let me pop up to the Data Analytics Toolpack, grab the regression tool. Wait, just before I do that, I've got orders, I've got month. I would like one more variable. So I'm going to take this column here, I'm going to say insert, and I'm going to say month squared. In order to estimate the quadratic trend, I'm going to need month and month squared. Month squared is easy, it's just equal to month. Raise that to the power of 2. 1 squared is 1. 2 squared just give me 4. 3 squared gives me 9. 4 squared gives me 16. And month squared are now essentially x1 and x2. I will include both of them in my next regression model in order to fit a parabola to this data instead of a linear trend. Okay, let's do it. Data analysis, regression, okay. Input Y range is going to be orders over here. Let's take all of those. And then input X range is going to be month and month squared. Let's take all of those. I've got everything highlighted. Line fit plots. Oh, look what we've got. Residuals, residual plots, line fit plots. I'm going to grab the residual plot. I can't resist. And yes, I did include labels. Okay, I send it, and Excel gives me some very interesting things. So here is the line fit plot for orders and the line as a function of month squared. And I will be the first to tell you that putting month squared on the x-axis, if you had x1 and x2 and x3 that were more real data, that makes sense, but I don't really care about the month squared one because I've got the one that uses regular month. And so I'm going to go ahead and discard that as if it was extra. I'm going to zoom in on this one that used regular month, and you see, sure enough, orders as a function of month. Here's my actual data in bluish, and here's my fitted in this orange color. And yeah, you can see right here it pauses and it starts to come back down at the end of the sample. So that's what a parabola is always going to do. It's always going to turn around somewhere. Okay, well, I've seen enough of that, but look at this. Once again, month squared on the x-axis is not that interesting. Here are the residuals as a function of time. These need to be unpredictable, like we were talking about a moment ago. I don't want to see predictable variation like any sort of oscillation or sinusoidal behavior in these residuals. I want to see pure randomness. I do see a collection of negative error terms here, and then a couple positive, and then a couple negative, and then a couple positive, and then a couple negative, and then positive, negative, and then positive. That's not supposed to happen. That's the seasonal pattern that I'm picking up in this data that this model is not accounting for. So I did miss something. The errors are correlated with each other. They are larger in the sense of being predictable than they should be if I had accounted for all of that variation. So R squared is too low, the standard error of regression is too high, my confidence interval is too large because this model is just not very good at fitting this data. But that's the way it goes. All right. Are there other data out there that a quadratic trend would fit pretty well? Sure, of course. But we're just trying this out for science. Now, let's say a couple of other things here. Once you get to your 95% interval forecast, I'm going to need a point prediction, and then we'll say your lower bound is your point prediction minus 1.96 standard errors, and your upper bound is your point prediction plus 1.96 standard errors. Of course, this is the cute theoretical version of that. your point prediction will actually be something like y hat and y hat over here, and then you have the standard error of regression is what you'll plug in here. If you're wondering what t plus ht is, that means it's the forecast of yt plus h that you made using data from time t. It's just a fairly typical notation in forecasting. Let's try one out. So I've got the data here. I've got intercept, coefficient for month squared, and here they are. Observation number, predicted value. This is for the quadratic model. So I'll go ahead and delete that first observation, and then let's make sure I can recreate it. So this should be equal to the intercept plus beta 1 times t, which is this number here. So we'll say beta 1 times t plus beta 2 times t squared. Now t is still the same variable, and I'm going to grab that there and then square it exactly this way. I don't have observation and then observation squared down here, but observation squared is just this number squared. So I'll do it in the formula. That's the way to do it. And that looks like the right number. Now I'll jump right back in and I'll say I want to make sure that this B17 doesn't move if I click and drag. So let's make sure that B17 doesn't move, let's make sure B18 doesn't move, and let's make sure B19 doesn't move. A26 can move as I click and drag this down, but this 86.378 is the right number. I'm going to click and drag and make sure I get 87.2905, this next one. Apprehension. There it is, it's the right number. Okay, then all the rest of these should be easy to replace with the right number. And they are, and I'll go ahead and just send it all the way down. Now here's my last observation. I can forecast as far out into the future as I want to using this model. I think I'll go ahead and get a little bit crazy with it. I'm going to predict another year of data. So here's 3 months, 3 more months, and then 3 more months. I'll click and drag that all the way down to the end of the 5th year of data, which of course I don't have, but here are my point predictions. And if I want to generate a confidence interval, I'll just use that estimate plus or minus 1.96 standard errors. The relevant standard error is the standard error of regression, which has to do with the size of these residuals. It's a little bit more obvious because the parabola, the slope of the parabola, is going to continue to increase as we get further away from the inflection point, right? So that squared term is going to start doing all the work. And I see that this thing sort of leveled off, 105, 104, 103, 102, 101. I do wonder how quickly this is going to go wrong, very wrong. So if I just go ahead and click and drag and get a little bit too far ahead of myself, yeah, sure enough, this model is predicting negative 890,000 by 340 months out. Well, that's a ridiculous amount of time into the future. So let's just go and look and see where it hits 0. This model is predicting that my orders turn negative by month 140. So in just a couple of years, this model predicts that I am going to be out of business. I don't like this model anymore because I don't want to go out of business. But I'll go ahead and calculate a lower bound and an upper bound here. Let's say my lower bound, well, let's give them names first. Lower, upper. For what degree of confidence? Let's stick with 95% and use the 1.96 as the critical value. So this will be equal to the prediction minus 1.96 times the standard error, which is going to be that number right there. 62.4. So the first observation should be somewhere between 62.4 and, if I take this formula and bring it over here, just switch that over to a plus. Upper bound 110. Well, I'm sure that it is. The residuals are pretty small, so yeah, looks like it's definitely in that range. I'm going to go ahead and bump this one over to make sure that B7 doesn't move. I need B7 to stay put if I decide to click and drag this all the way down. And the same thing here for this upper bound. B7, I want to stay put. I'll double click, and I'll double click over here. And now I have point forecasts extrapolated all the way out to, frankly, a ridiculous length into the future. And I have interval forecasts extrapolated all the way out into, frankly, a ridiculous length into the future. But you see them here. They're just the point forecast plus or minus 1.96 standard errors, which is the way we do this. There is a bit of there's something to say here about parameter estimation uncertainty. Okay, that would be a difficult thing to accommodate here, but we are entirely ignoring the fact that beta 0, beta 1, and beta 2 are estimated with a certain amount of precision on their own. So we're not allowing that to contribute at all to these confidence intervals. So it's a little bit, we're missing something. It's a little bit wrong, but this is the easy way to do it, and it's reasonably common to do things this way. And for a class like this, we're just going to roll with it. Fair enough. But comparing the linear trend and the quadratic trend for these two models raises a couple of sticky issues. When we talk about model selection, how do you select the best trend among many candidates? Is the linear trend or the quadratic trend going to be better in this context? Well, I know that I could, for instance, look at R-squared, but R-squared is always going to choose the larger model. Let's verify. R-squared for this quadratic model is 0.194. R-squared for this linear model is 0.172. R-squared chooses the quadratic model because R-squared always chooses the quadratic model. All right, what are my other options? Well, I want a smaller standard error, and I want a smaller adjusted, a larger adjusted R-squared. So I could consider using one of these to choose the model. That's not bad. The adjusted R-squared has a degrees of freedom penalty baked into it, so it actually can get a little bit worse if you add a variable to the model that has no explanatory power. It's possible for adjusted R-squared to go down. It's rare in practice for that to happen, and here I see 0.158 adjusted R-squared for the linear trend was 0.154. So adjusted R-squared, like regular R-squared, slightly prefers, I say slightly in the case of adjusted R-squared, for the regular R-squared it was not that slight, right? But adjusted R-squared prefers the quadratic model. Now, if I look at the last of these three regression overall fit statistics that we have up here, between the linear model and the quadratic model, the standard error of regression, which is a standard deviation of the residuals, barely moves. It is better in the quadratic model. Okay, so adjusted R-squared, R-squared, and the standard error of regression all seem to prefer the quadratic model in this case. But how big is that difference for adjusted R-squared and the standard error of regression, really? It seems kind of negligible. And when we talk about forecasting, there's a very, very strong propensity to stay away from the big models. If you have two models that have about the same goodness of fit and about the same explanatory power, but one of them is simpler, we really want to put our thumbs on the scale and go for the simpler model. It's going to do better if we try to forecast even a little bit further out into the sample. So there's a very strong push. Well, okay, model selection based on measures of goodness of fit such as R-squared does not lead us to choose good out-of-sample forecasting models in general. That is a sobering statement. What can we do? Well, the idea goes like this. There are a whole bunch of statistics that can be used for model selection, things called model selection criteria, and they're all kind of based on the idea that you're just looking at the variance of the next error term. So the variance of the error terms would be something that we call sigma squared, right? Variance of the error term conditional on whatever information you use to predict yt, which is what this is saying. The variance of the error term should be as small as possible, but you should do it with the simplest model possible. Okay, well, how do you split the difference? Each of the model selection criterion we're about to look at is going to prefer a smaller value. A smaller value for a model tells you that that model is better, in a sense. And we start off with just the easy one. And as it turns out, the good model selection criteria, which we don't use so much, except if you become a professional forecaster, then they're a big deal, or if you read serious forecasting papers. But all of the real good model selection criteria use a penalized version of the mean squared error. You know that I love the mean squared error. It's one of my favorite statistics. It belongs to my favorite class of statistics, which are the statistics where the formula for the thing is in the name of the thing. So in this case, I take the error. Here it is, I found one. I take the error, I square them, I add them up, and I divide by how many there were. That gives me the average of the squared errors, which is the mean squared error, average squared residuals. And I do want that to be small because this tells me essentially how large the errors are. Well, hop back to Excel and look at any one of these. The residual sum of squares, right here, this is the sum of squared residuals. If I scroll down, and of course I've made a bit of a mess here with these extra forecasts that I made. So I'm going to clear this column and buy myself some space and say squared residual. My squared residual in each of these is equal to that number, raise it to the power of 2, hit enter. There, I've got a squared residual. And I'll go ahead and send that all the way to the bottom. Of course, the rest of these are 0 because there's no residual for those observations. And I don't need these forecasts anymore, so I'll do that. If I want to know the average of these squared residuals, I simply add them up and divide by how many there were. I'm going to do two versions of this. I'm going to say SSR, which is the sum of squared residuals, and then I'm going to say MSE, which will be the mean squared error or the mean squared residual. So if you want me to call it MSR so that it goes along with SSR, we can do that. Well, I'll kick this over to E, sum of squared errors now. And then MSR will be MSE. As is often the case in statistics, we have to have at least two different names for the same thing. So the sum of squared errors for this column of squared residuals is just going to be sum. That's a squared error. We go all the way to the bottom, close the parentheses, hit enter. How big is the sum of squared errors? 6734.5928. That number there is the sum of squared residuals, as you might guess from the sum of squared residuals. All right, SS, residuals, sum of squared residuals. And then the mean squared residual. This number is the sum of squared residuals divided by the degrees of freedom, which is n minus k, or in this case, t minus k. That's a bit different from what we have here. This is regular old mean squared error with no degrees of freedom penalty. Divide by t, don't divide by t minus 1 or t minus k, just regular old t. All right, well, I'll do it, and I'll come up with a number for that. Let's say equals average of these same squared residuals. Send that all the way to the bottom, close the parentheses, 140.3. If I had said instead equals the sum of squared errors divided by 48, of course I'd get 140.3. If I had said equals the sum of squared errors and divide by not 48 but 48 minus 3, which is the degrees of freedom, I'd get 149.657619, which is this. All right, that's the reasonable thing to do. That's where the standard error of regression comes from. It should be the square root of that number, because this is essentially the variance, the estimated variance of the residuals, and the square root of that will be the estimated standard deviation of the residuals. But the regular old unpenalized mean squared error is our starting point, because this is 1 over t times the sum of squared errors, which is what OLS minimized in the first place, all the way back in Module 1. So I want this to be as small as possible because that's the whole game that we're playing since Module 1. The first thing that we think to do here is bring in that degrees of freedom and say t minus k, because if I have a very large model, subtracting k in the denominator will make this larger. If I have a large model that doesn't explain the error terms better than a small model, MSE with t minus k in the denominator might actually get worse. So there's some conversation here about why there's also an unbiased estimator of those sigmas, but that's what we're going to do. All right, so the variance of the residuals will be this corrected, this penalized degrees of freedom penalized mean squared error, which is typically called something like s squared, which is the square of the standard error of regression. Okay, so that's actually a better estimator of the variance of the residuals. But when we talk about r squared was this formula, 1 minus this ratio, without the t minus k here. Adjusted r squared, which we've seen before, is 1 minus the sum of the squared. These are the errors. And in the denominator, it's the sum of the squared. This is the total sum of squares. Adjusted r squared has the t minus k here, and the t minus 1 here that goes along with the total sum of squares. So it's the variance of y in the denominator and this better estimate of the variance of the residuals in the numerator. The point to be made here is that the degrees of freedom penalty in the numerator for adjusted r squared, t minus k, that's the same as putting s squared here, this guy, that degrees of freedom penalty is exactly the same as the degrees of freedom penalty that's baked into the standard error of regression, which is just the square root of this guy. So if I go back to this top of the table, I know r squared will choose the largest model. It always chooses the largest model. These two actually choose the same thing, minimizing the standard error of regression to try to choose a model, or maximizing adjusted r squared to try to choose a model will always lead you to choose the same model, because adjusted r squared, this whole formula, basically has the square of the standard error of regression baked into the numerator here, and something that doesn't care about degrees of freedom baked into the denominator there. Okay, what else can we say about this degrees of freedom penalty, t minus k, that is used in adjusted r squared and the standard error of regression? It's very weak. It exists. It is a degrees of freedom penalty. These two statistics tend to prefer, very slightly prefer, smaller, more parsimonious models. From a forecasting standpoint, that's helpful. But their preference, their bias towards the smaller models is essentially negligible, and it's not good enough to actually use them for model selection when we're talking about forecasting out of sample. That's actually the big point of this part of the video, talking about model selection criteria. When we talk about model selection criteria, unfortunately, none of these in Excel is actually adequate for that task. Can you choose a model based on r squared, adjusted r squared, and standard error? Sure. Will it probably be too big? Yes. So just to sort of fill in the blank and say, what could you do instead? Well, there are other statistics that will use something like the original mean squared error and then apply some penalty to that, some function that gets larger as you use more degrees of freedom, as k gets larger. So if I use a model that has 4, 5, 6 parameters, this penalty should get very large very rapidly. Two of the famous versions of this approach, there are actually quite a lot of these, and in fact, the really good one, the Schwartz information criterion, which is also called Bayes information criterion, is not unique in the good property that it has, where if there is a true model, asymptotically, as you get enough data, it will choose the true model. That's amazing, but it's not unique. AIC doesn't have that property, but the formula looks like this. We take MSE and we attach e to the 2k over t. So as k gets larger, this thing gets large pretty fast. SIC is a bit more radical. You take t to the k over t. Remember, t is the same thing as n in this context. So if you have a large sample, then this base in the exponential term is actually enormous as well. So t to the k over t times MSE. And they have slightly different formulas if they're written in logarithms, and the units on these things don't really matter. So if you're using different software packages, you'll see that they're implemented differently. The point is you just want to minimize it within a software package, within whichever way it is presented. And there's a picture that says the penalty for s squared or adjusted r squared as a function of k over t looks like this. It's very, very weak. The penalty for AIC is basically twice as strong. And then the penalty for SIC is way, 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 way stronger. And you see that function, that very strong penalty for the size of the model, is what you actually need in order to get the good behavior, where we say SIC is asymptotically consistent in terms of it will zoom in on the selection of the best possible model. If there is a true model among the models being considered, the probability of SIC selecting the true model in the limit as t goes to infinity, or as your sample size gets asymptotically large, the probability of SIC selecting the correct model gets close to 1. That's the best thing that could possibly happen. But all of that is to paint a picture and say, you need to be way more radical about rejecting the big models. And if somebody says, oh, I've got a quadratic trend, a cubic trend, a quartic trend, a quintic trend, some sort of a very large polynomial trend, like we're doing here in these slides and talking about these deterministic trend models, especially when you've got something like 48 observations, I wouldn't dare estimate a model with maybe more than, well, maybe 3 parameters, but the more parameters I add, I'm just burning through degrees of freedom. Right? I've only got 48 observations to begin with, so a model much larger than 3 or 4 parameters is starting to be something that I think is a little bit dubious. And unfortunately, when we get into the next topic, which is seasonality, and I start trying to come up with ways to model how the different months are different from each other, I've only got a couple of observations of each month in this 4 years of data. I have 4 observations of each month. So it becomes very, very tenuous to try to model the months individually with 4 observations for each one. So in a small data set, you really just have to stick to the simple models and don't try to do anything crazy, because the crazy models that might perform well in the data set are going to fall on their face when I try to forecast out of sample. You get to try that with things like quadratic and cubic models. And it's not super far into the future, but I did see that this quadratic model is going to predict orders going to 0 not too far into the future. So that's a bad sign. Right? So SIC is consistent. AIC and SIC are both fairly common in the literature if you do look at real forecasting. And I can point you to a couple of papers that use AIC or SIC for model selection outside of the forecasting context. It is preferable to R squared or adjusted R squared or the standard error of regression. But what do we have to work with in Excel? Things that are a bit more mainstream. We have R squared, adjusted R squared, and the standard error of regression. And hopefully at the end of this video, some fairly solid sense that none of these are actually going to help you choose the model that well. You can still interpret R squared and adjusted R squared as the proportion of the variance explained in the model, or the standard error of regression as the size of the error terms, and larger R squared and adjusted R squared is better, smaller standard error of regression is better, but these things tend to choose, all 3 of them, tend to choose models that are too big. Okay, I will end this video there and see you soon in the next one.